Greetings from India. You are listening to the Businesstalk podcast. I'm Deepak, your host for today's episode. We are delighted to welcome Dr. Swati Gupta, class of 1947 Career Development Associate Professor and an Associate Professor in the Operations Research and Statistics Group at the MIT Sloan School of Management, as our distinguished guest on today's podcast. Dr. Swati's research lies at the intersection of optimization and artificial intelligence, where she develops algorithms and learning methods to address real-world challenges involving incomplete data, multi-criteria decision-making, and quantum optimization. Her work spans sectors such as healthcare, supply chains, and e-commerce, and she actively collaborates with industry and academic experts. She leads the Ethical AI Trust at the NSF AI Institute on advancing in optimization and has received awards including NSF Career Award, JP Morgan Early Career Faculty Recognition, and the Google Women in Engineering Award. Dr. Gupta is an associate editor for the Open Journal of Mathematical Optimization and has served on the program committees for top conferences in optimization and AI. Dr. Swati earned her PhD in Operations Research from MIT and holds a joint master's and bachelor degree in computer science from the Indian Institute of Technology, New Delhi. In this episode, Dr. Swati Gupta shares insights from her research, Ethical AI in Healthcare, enhancing clinical decision support through interpretable machine learning and responsible error handling in EHRs, exploring how ethical and transparent AI can transform healthcare decision making. So without further delay, let's welcome Dr. Swati Gupta to the podcast. Dr. Gupta, it's been a true privilege to host you today. Thank you for taking the time to join us and discuss your work.
Thank you, Deepak, for having me here as a guest. I'm delighted to speak to you and your audience.
Dr. Gupta, what inspired you to focus on interpretable machine learning specifically for clinical decision support? And how did the challenges in electronic medical record data shape your approach?
So, I'm interested broadly in understanding what are the unintended consequences of using AI and machine learning in a lot of applications. So, these methods are using data that is noisy, that is errored, that could bake in some societal biases. And when we use optimization or we try to do some decision analysis on this data, it can create some unintended consequences on a diverse set of people. So, in particular, I'm interested in the healthcare setting because the decisions are so very critical. They're critical for saving lives. And sepsis is one of the leading causes of deaths in the US. And this is why we wanted to focus on interpretable ML for error handling in electronic medical records data. So, interpretable is very important in healthcare specifically because doctors, as experts of the domain, have to trust the decisions of the model. So, if you want an AI model to actually be implementable in practice, then it has to have the ability to explain why it is maybe suggesting a particular prescription, draw from perhaps past patients, past case histories, explain why the model is making certain decisions. So it's not a black box anymore. And this is true for many domains where people have a lot of domain expertise. And so to integrate AI within those decision-making systems, we want a human AI collaborative system.
Could you explain in layman's terms what trust maps does and how it differs from traditional pre-processing or anomaly detection techniques in healthcare data?
Okay, so the traditional techniques of imputation or correcting errors, what they'll basically do is they'll learn from some past data. They will try to create models that interpolate from past data. So let's say, your your heart rate is recorded as 60, then 65, then 70. Then there is a missing entry, and there is a missing entry, and it goes back to 60. So what these methods are going to do is they're going to, first of all, form a linear interpolation. So they're going to say, well, between 70 and 80, you didn't have a recording, and so it must be 75 because the rate is dropping over time, right? So existing methods in this space will learn from past patient data, it'll learn from trajectories, it'll try to do interpolations, they try to implement methods like mice, which will spawn various models and try to fit the data. What we are doing is something very different. So we came to this problem thinking about um, the way clinicians read this data. So when a doctor looks at your chart, they will say that, okay, it seems like the patient was on the ventilator, but oxygen is not recorded as being back to normal, but it should be. So they can take in the context of all of the other labs into account and not just focus on a single lab or a single vital. And so our goal here was to understand, how do the doctors automatically in their heads correct that data, and they don't rely on something as simple as imputation methods, right? And so we talked to a lot of clinicians, we created mathematical constraints. So we tried to kind of encode their domain knowledge into something that is very mathematical. So, as an example, if lactate is greater than 6, which is one of the labs, right, then bicarbonate better be less than 0. That is something the clinicians told us, that that's the relevance between lactate and bicarbonate. And so instead of just focusing on how is lactate varying over time and imputing that, we look at cross relationships between different patient vitals and take those dependencies into account. And so that is one piece of it, right? So we say that, what is the data? What is the potential space that the data for any living person can lie in? And we call that one possible set of the data, that our data has to satisfy certain constraints and relationships. And then we talk to the clinicians in understanding, how does a not critical patient look like, how does a homeostasis, it's called, how does a normal physiology or not a critically ill patient look like. So once we model these as high dimensional mathematical regions, we are then able to understand, create more information, a meta information about how sick different patients are based on the deviation that they have from normal physiology. And that makes a very important information for downstream prediction and downstream early warning systems like the one that we are trying to develop here.
Professor, how do you translate clinical domain knowledge such as
Mhm.
physiological norms into mathematical constraint for machine learning models?
Right. So, as an example, right, like as I mentioned, for if lactate is greater than 6, then bicarbonate must be less than 0. Or the heart rate of a person can only change by a certain number of units every hour. Or the pH level can only change by a certain rate, right? So we spoke to the doctors and we converted these into if then else constraints. So mathematically, we there is a beautiful way in optimization to convert an if then else statement by using binary variables. And so we convert all of these into a bunch of mixed integer constraints for a mixed integer region, and which basically encodes in layman terms, constraints like, if pH is less than 7, then either bicarbonate has to be less than 10, or another vital has to be less than 35. So again, it's in capturing the dependencies between the vitals of patients as they move through time, and also across any slice of time, what are the relationships that different labs should have. And then we correct this data by using a technique called projections. So if you're interested, I can explain that more.
Sure, please.
So imagine that you're standing on a chair, and you take a ball and you throw it on the floor, right? So you just drop it on the floor. So what is the point at which it hits the floor? That's the closest point from the ball in the air to the floor. So now think of all of this clinical constraints that we developed from a mathematical perspective. that all of that data lies on the floor. But when a patient's data arises, it's like that ball. It's not in the floor because it's errored. And so we try to find that point with the shortest distance in that in that set of feasible data points. And so that's mathematically called a Euclidean projection. So we can compute projections by by solving an optimization problem. So we can correct the data while accounting for dependencies across vitals and labs.
As AI systems are deployed in healthcare, finance, hiring, and law enforcement, how can we ensure that algorithms are fair, unbiased, and do not unintentionally reinforce existing societal inequalities?
So this is a very challenging question to answer, specifically because, in different domains, there's very domain specific challenges that appear, right? So in the healthcare setting, for example, I just talked about there is recording errors in healthcare data, there is errors in the labs, there is errors in the labs that could be correlated to the skin tone. Like there is a pulse oximetry measurement that depends on the changes in blood flow, and it is measured by shining light through your nail. And so if the color of the skin actually then creates a difference or a variation in the accuracy of this measurement, right? So in but in another setting, like let's say hiring, you mentioned, the errors might come from a very different source. So it could be because of different opportunities that people have got in their training, because of the kind of test preparation that they've done, because of the way they learned how to write resumes. Maybe the way that the resumes are being read is very, it's picking up on certain characteristics that not everybody knows or has access to, right? So depending on the domain we are talking about, the challenges are very nuanced, they're very different. But at a high level, I would say it's basically because of noise or errors or systematic or some correlated errors in the data. It is because our proxies may not be well aligned with what we want to measure, or it could be also because our objectives are prioritizing something that is more that is not equitable or efficient, or it's prioritizing efficiency more than feasibility, or having equitable access to resources and things like that. So I would say that to mitigate these problems, one has to really understand what is the how does the application kind of work? How is the data generated? What are the kinds of decisions being taken? How can we take decisions that are more robust to the errors? Even if we know things are noisy, even if our measurements are noisy, how can we still take more reliable decisions? And another layer to it is interpretability of decisions that are taken by AI, because AI models might be more certain or more accurate on some populations, they might be less accurate on some other populations. And so kind of one of the things I'm trying in my research and my vision is that the AI systems that we deploy should be very transparent about the errors they are making on different input data, so that we can, as humans, we can decide whether to use that prediction or to defer to a human expert instead and not use that prediction.
Professor, why do unintended consequences often arise in AI and machine learning systems? And what factors contribute to these outcomes despite careful design and testing?
So the careful design and testing, I feel like, okay, so I just talked about kind of noise in the data. It could be because of noise in the AI predictions that are then used in downstream data. And so I think in a deployment of an AI model, one has to be very careful about incorporating different checks at different points in the pipeline. So it's not just enough to debias the initial data. It's not just enough to have a single model that kind of predicts something, because the predictions of these models then are are used in downstream tasks as well. So I think one has to be careful about that entire deployment process.
Dr. Gupta, the concept of trust scores is central to your method. How are these scores calculated and why are they important for both interpretability and predictive performance?
Very good. So the trust scores that are created are basically in this, so kind of going back to the healthcare data that we were talking about. We call trust scores as these scores that are computed on corrected data. So first we take the patient's data that might have errors in it. Then we find the closest data point that satisfies all of the clinical constraints. Then we take what might be the closest data point, which is in the homeostasis constraint, which is the set of constraints that model a not sick patient, a normal physiology patient. And so we call these trust scores are trustworthy distances between corrected patient's data and normal physiology. So, for example, if I say that, heart rate between 60 to 120 is normal and beyond 120 to 200 is abnormal. So, if a patient has a heart rate that is closer to 200, then that means that they are sicker, or maybe they're having a lot of cardiac stress. If the heart rate is closer to 120, then we know that, okay, this is closer to normal physiology, or 130, it's closer to normal physiology. And so they're not in a cardiac stress right now. So depending on what is the variation of the patient's vitals from normal physiology, we can create these trust scores that tell us how sick the patient might be.
EMR data are notoriously noisy and biased. How
Mhm.
does trust maps handle errors and mitigate biases that could otherwise lead to incorrect clinical decisions?
Right. So because of the correction with the dependencies between different variables, we are able to impute missing variables much better. So let me give you an example, maybe with a picture.
Sure.
Here, can you see my slide?
Yes.
So in this example, we are creating a relationship between mean arterial pressure, diastolic blood pressure, and systolic blood pressure. And it is known that the mean arterial pressure is a weighted average of diastolic and systolic. And so let's say that this is within like a 5% error. So those are the two constraints that we will have in our system. And when you look at the way we impute it, if diastolic data was completely missing, it would be imputed at the mean value, which is that red line. But actually noting the variation in the mean arterial pressure and the systolic, diastolic should actually vary as that blue line. So you see that we are able to actually utilize the relationship between these different variables that move with time more effectively with this technique.
Professor, your paper demonstrates a 15% improvement in early sepsis prediction. Could you share why this specific task was chosen and what the clinical implications are?
So, Deepak, sepsis is the leading cause of morbidity in the US and also globally. And its cost to the US healthcare system has been increasing significantly. In 2013, it accounted for more than 24 billion in hospital expenses and representing around 13% of total US costs. And today, the market for early warning system for sepsis has reached 1.13 billion in 2024. So, sepsis is a disease in which once there is an onset of sepsis, there is multiple organ failure that happens. So, at that point, if the doctors now start treating for, let's say, kidney failure, then the patient might go into a heart problem, cardiac stress. If they start treating that, then they might go into lungs and so on, right? So, once multiple organs start failing simultaneously, then it's very hard to control the patient's trajectory. And so for sepsis, so what we are doing here is that we are able to predict 6 to 8 hours before onset. So that is what makes it very valuable. That if we warn the doctors that, this patient's trajectory is deteriorating over time. So imagine scenarios where, the doctors are not able to very carefully monitor every patient, or they would like to have more critical patients be highlighted to them so that they can take a more careful look and try preventative course of action, then we can save a lot of lives. And this is why we decided to think about the correction system and the enhancement of downstream prediction tasks for this very critical disease.
With AI making increasingly high-stake decisions, what
Mhm.
framework or principles should guide transparency, explainability, and accountability across diverse applications to maintain public trust?
That is a great question. And I think AI being transparent about where it is able to actually. So, see, where is AI the most useful? It is most useful in crunching a lot of data, in finding patterns, and generalizing those, and prescribing things. It is amazing at that. We cannot expect humans to go through millions or billions of records on patients and then try to create patterns out of them, right? Humans are much better at understanding the contextual knowledge in discounting certain data if they don't think it is reliable. So humans are very good at that. And so I think the key to making interpretable, explainable, trustworthy, transparent systems is that they are transparent about where are they making more errors. So instead of an AI system just saying that here is my prediction, if the AI system says, here is my prediction, and I am 80% confident about it, or here is my prediction, and I am only 20% confident about it, then that is a very valuable information for the human who's in that loop of making decisions, because then they know when to not trust the AI system. I think in today's industry, what is happening is people have just a blind faith in the AI model. They will say, well, that's the AI prediction, so it must be correct because the overall accuracy of this model is, let's say, 95%, right? But where is it making those 5% of errors? And can we actually point out where those 5% errors are concentrated? Can we then deflect instead of making a decision through the AI system? Can we be more, make more a better decision or collect more data or find a different approach for the 5% of errors that the system is making? I think that's one. The second thing is to understand, as you're driving a car, that if you turn your steering to the left, the car is going to go to the left. If you turn your steering to the right, it's going to go to the right, right? And so for an AI system to be trustworthy, one has to have checks and balances that can check kind of the left and right orientation of these systems, right? So, for example, if I create a fake patient and this patient has very high cardiac arrest, this I know that this patient has a, a high variation in all of the vitals, then the system better predict, yes, they're going towards sepsis, right? And so, in some sense, to check for consistency and robustness across a lot of these left right kind of um, variations to data, even if we may not have that data in our training or test sets, but to check for some sort of a consistency check in the AI system that tells us, yes, it is operating like we expect it to operate. The curious thing is, like a lot of people work in areas like adversarial ML. There is a lot of research in that. And what's happening is that if you take an image and it says, let's say, a stop sign or a red, so stop signs in the US are for asking the traffic to stop. But if you add a random noise to it that visually looks like it's still a stop sign, the prediction of the system might say that now it's not a stop, but it's actually go at 30 miles per hour, right? And so in that case, AI is kind of failing that safety check that if something looks like a stop sign, it should still predict a stop sign, right? And so I think it is very important for building trustworthy systems to know what are the dynamics of the AI, how do we expect the decisions to change, and cross check those with the AI systems before deployment so that we can get ahead of unintended consequences of these systems.
Dr. Gupta, how can hospitals or healthcare organizations integrate trust maps into their existing machine learning or clinical decision support systems?
Thanks, Deepak. That's a great question too. I think so. The module that we've developed is it's quite modular. This technique is quite modular. So for any machine learning system that uses patient data, that uses data that can potentially have errors, then they can hospitals can plug in our trust maps as a module to that pipeline, and that will definitely improve downstream ML. The way that they will plug it in will require a little bit more work, which is what we are doing in our research right now. But for example, for sepsis, we've already talked to a lot of clinicians and we've created kind of this database of constraints. But for other diseases, we might need to incorporate those constraints more. So I'm actually very excited in my research to talk to a lot of hospitals and clinicians looking at various diseases and create early warning systems for these.
Sir, were there any unexpected challenges in implementing trust maps or translating clinical knowledge into algorithmic constraints? And how did you overcome them?
Okay, so this is actually interesting. When we think about mathematical models, they are very well defined. They don't have missing data. Everything is as simple as defining a number and then fixing that number and proving things about it. But when it comes to applications, then the data can be very varied. It may not meet mathematical assumptions at all. So, for example, often when we think about projections, we think about a fixed number of dimensions. Like the ball being projected to the floor, everything is happening in 3 dimensions, or your dimensions of the data. If we think of 100 vitals being measured for a patient across 8 hours or so, we would have 8 times 100, 800 dimensional data, right? But what we saw in the actual data from patients in an ICU, they had varying lengths of stay. So some patients were there for 6 hours, some were there for 24 hours, some were there for 36 hours, some were there for 20 hours. And so the amount of data that we had on patients was not the same. And so this was a puzzling question, like, how do we compute, how do we set up this optimization, how do we find the corrected data if the duration of length of stay is not the same across everybody. And so we realized that actually the way we overcame that is by dividing every patient into a segment of 6 hours that were overlapping. So now think of a patient's ICU stay from 0 to 10 hours being divided into from 0 to 6 hours, from 3 hours to 9 hours, from 6 hours to 12 hours, where the last 2 hours we don't have that data. So we segmented every patient's stay in the hospital in a period of 6 hours. So now we could have a fixed dimension to work with. There were many such challenges, but that's what's exciting about working in this area. There are challenges that we don't anticipate, and then when we see them, we have to think about new solutions to them on the fly. Another example was that when we were creating kind of these trust scores, we realized that for some patients, the trust scores were very high. And so we realized, so when we looked at that set of patients, we saw that, these were all patients where calcium was recorded in the wrong units. And this is why we were getting this thing that they have very high errors. So we were able to then kind of talk to the doctors again, find out why was there so much error in the calcium values across this group of patients and everybody else. And we realized it was the wrong units. In some other patients, we found that the person who was recording the data forgot to place a decimal point. So instead of something that should have read 0.40, it read 400 because they didn't put the decimal point in the system. Now, when a doctor is reading that, they will say, oh, but this value cannot be 400. It has to be either 4 or zero point 0.4. And they might order another lab to check that, right? But when you're training machine learning and AI models, they don't have that context. So I often say that, AI models don't have a 20 by 20 vision. They are not able to see our world perfectly. They only see our world through the mathematical models and constructs that we formulate. And so, to make them more accurate, our modeling has to be more accurate, or it has to mimic the real world. So, if we can give some of the context to these, they'll be much better. But and this is why also, because I don't think we can give always all the context that is there. Having humans in the loop with some frequency is important.
Thank you, Dr. Swati Gupta, for sharing your insightful research on interpretable machine learning and error handling in clinical decision support. Your work with trust maps not only demonstrate impressive involvement in predictive performance, but also highlight the critical importance of trust, transparency, and clinical context in AI applications. As we continue to integrate AI into high-stake domains like healthcare, your research reminds us that innovation must go hand in hand with interpretability and ethical responsibility. We hope our listeners leave inspired to explore how machine learning can be both powerful and trustworthy. Thank you once again, Professor Gupta, for joining us.
Thank you. It was my pleasure.